Hello everyone, this is Universum, the place where I learn about the entire universe, how it began and how it will end. Today we are going to be talking about gradients and vector fields and what do they have to do with quantum mechanics and basically just physics in general. Alright, so let's get started, I guess. So what a gradient is in terms of vector calculus is that's basically you're defining a scalar field representation. So like for instance, usually in vector calculus you'll see it denoted as the Greek letter nabla, which just looks like an upside down delta, or if you don't know what delta is, an upside down triangle. Otherwise, now the gradients, it has a rather simple definition. Basically, you just take the gradient of a function, that's going to be equal to the differential of that same function over the differential with respect to that function of 1, and then basically just keep on taking partial differentials of the same function until basically you get to the nth derivative. And well, that basically is the basic definition of it. Now, if you guys want to explore vector calculus in a little bit more further detail, there are a few books I do recommend. Now, if you're just looking for general calculus in general, I probably would recommend this book right here. Calculus 1 and Several Variables. It covers all fields of calculus. I know it's a little bit on the older side. It was made in the 1970s, but still. But I mean, it's a really good book. It provides some nice representations. And all right, getting away from the book and getting back to our conversation on gradients and what they have to do with quantum mechanics. So now you might have seen this so-called nabla sign in many different equations. So there's the Schrödinger equation. The Schrödinger equation, well, that basically just is defining the wave function. So like, for instance, there are many different types of Schrödinger's equations, the most famous of which is just h bar, which is just an energy, not h bar, h hat, or the Hamiltonian operator, and the Hamiltonian operator is just simply just defines an energy eigenstates. Then there is psi, which is the wave function, and that's going to be equal to the same energy of that psi wave function. And so basically, then you're wondering, why don't we just use the energy eigenstate in the first place? Well, we usually use E to define a little bit more. We usually use H, which is the Hamiltonian operator, or H hat if you want to describe it in a little more detail, as a little bit more general terms. However, you might have seen it in some equations, such as some more complicated ones to represent more, like for instance, if you're imagining imagining imaginary time, such as quite a complex one was going to be I h bar, first differential with respect to the differential to time, and then of course this is representing the time evolution operator, and that's going to be with respect to the wave function to represent the wave function as it goes on, as it fluctuates throughout time evolution. R of t, basically that's going to be position and time, and that's going to be equal to negative h bar squared over 2m. You might have heard of this operator tons of times in quantum mechanics. H bar squared, that's also just going to be Planck's constant yet again. It's just a boundary condition operator. And then over 2m, that's just simply just going to be reversing the phases. And then this one gets to the nabla operator. That's going to second derivative of nabla. So you're probably wondering, why is nabla here? Well, nabla isn't just used to represent gradients and vector fields, but it also is used to represent the Laplacian of the wave function. That's why it's with respect to the wave function. So nabla squared, basically, now, or you can simply just call it the Laplacian operator if you really want to. There, of course, as with the Schrödinger equation, there also are many ways to represent the nabla operator. The most common way to represent it is the second differential with respect to the differential of x squared plus the second differential of you basically in a nutshell, you just are representing the wave function with respect to Cartesian coordinates. Anyways, getting back on topic. Basically, it's a second differential with respect to the second differential of x squared, and that's going squared simply just means what differential you're talking about, plus the second differential with respect to the differential of y squared, plus the second differential over the differential of z squared. Yeah, that basically is what the Laplacian is. And you're probably wondering, well, at least a few of you are wondering, in case you don't know what it is. Well, what is that? Well, how do you represent that? Now, the Laplacian, it can be described in many different ways. Like, for instance, Laplacians, of course, they can be represented in Cartesian coordinates, as I just have said. All right, and then the Laplacian can be represented, of course, in wave functions, or such as in this one, you can imagine it in an imaginary Cartesian coordinate field, such as we just defined, Planck's constant. Anyways, and then after the Laplacian with respect to its wave function over the respect to time, basically just respect to the particle's position and time, you can use this for many, many different things, such as Pauli exclusion principle, such as two particles in a box. They're trying to represent both of their different wave functions. And if you're trying to represent their two different wave functions, then what you can do is that, well, we're trying to, basically you can just multiply the wave functions by one another, and then you can just measure the amplitude from then on out. Basically, the wave function is just representing the amplitude of a particle in a so-called simple harmonic oscillator. All right, and then now getting back to the Laplace operator. So basically, in mathematics, the Laplacian is a differential operator, and basically this is another way of measuring divergence of a gradient of a scalar field. And of course, you have to make this work for Euclidean spaces, or else you use it for spherical coordinates, or if you use it for hyperbolic coordinates, it will sort of break down. So I wouldn't recommend it if I were you. All right, getting back to it now. So, all right, so usually a lot of times you will see the Laplace operator in many different fields, but the most things they'll see it in is this thing is called the heat equation. This is getting off of quantum physics. As I explained, one example in quantum physics. Of course, there are many, many, many more examples. And there are many, many, many different types of Schrödinger equations. Of course, in a nutshell, a Schrödinger equation just has to represent the wave function with respect to its time evolution operator. Of course, the first one I just told you was the simplest of all of them, which didn't really have to do with the Nobel operator, but, well, hey, the more you know. Okay, so another way to represent the Nobel operator is simply just going to be the change in a certain function, as I explained before, of course, which is going to be a simple one, which is just taking a gradient of a function, and then you simply just keep on just adding on those differentials until you get to the nth differential. All right, and then but in this one it's a little bit more simple. So what you have to do is you have to take delta of f. Yeah, of course you're having a right-side up triangle this time. Delta of f, or just simply change in a function, it's going to be equal to the gradients, the second derivative of a gradient with respect to its own function, and then that's going to be equal to the gradient times the gradient of that function, where basically the latter of all those notations will derive from a more formal type of writing, which is going to be similar, which is going to be basically the exact one I just told you before, which is simply just taking the gradient of that function, which then is going to be equal to its differential of the same function over the first differential of x, second differential, third differential, and so on and so forth, until it gets to the nth differential. All right, and then another way you can represent it is by representing it, of course, in Cartesian coordinates, as I told you, by representing the Laplacian in quantum form. In quantum physics, you can represent it in Cartesian coordinates, basically by doing the delta of f, or the function. The change in the function is going to be equal to the summations, all summations over I equals 1 to n. Of course, just taking nth derivatives now, again. Of the second differential of the same function over the differential of x squared sub I, which then you simply just use the indices, and they just keep on just going out until you eventually hit the nth operator. All right. Now, since we got the Cartesian coordinates over with as Gilson's, basically in a nutshell, in this summation notation, you simply can just represent the Cartesian coordinates as x of I. All right, because we finally got that out, now maybe you probably are wondering, well, what is the heat equation and how you represent the heat equation in Nobel operator, of course. Well, heat equation basically it just is well, it's basically nearly the same way that you may think it is, but it's a little bit more different than it may sound like, mathematically at least. I mean, basically, heat equation is just representing the heat transfer over one object to another. Basically, Fourier made his equation. All right, so the heat equation is Q sub T of V. So Q of V is going to be an operator that is going to be equal to the negative integral of the differential of V. V is going to be representing over time, and then that's going to be bold H. Because the H is going to be an important operator, which is simply just going to represent heat with respect to x times n of x ds. All right. Now, basically representing the heat equation. The way that you would represent this is with that equation right there. However, you could represent it in a little bit more easy ways. Like, for instance, there is more to add this to this equation, for instance. So if you're wondering, well, where's the nabla in this equation? Well, we're getting to that. So if you integrate it a little bit more, what you will get is that you'll get that is going to be equal to the positive integral, thank goodness, of the differential of V, A of x, instead of h of x. That's going to be another operator representing heat. And then that's going to be times nabla, which is simply just going to mean the gradient, as our described notation before, of u of x times n of x ds. Then if you want to simplify it a little bit further, that is going to give you the grand total of the integral of the summation of I and j. I and j are two indices. And then that is going to be the first differential of x of I, of course. Remember, x of I, that is going to be represented as a Laplacian. So now we know that the nabla operator in this equation is going to be a Laplacian, which can be represented a multitude of different ways. All right, and then in between brackets, that's going to be A of ij, of course, plugging those indices again. Just like you know, now if you're wondering why I didn't mention the upper bounds of it, it's because there's no upper bounds to it of x, and that's going to be the differential of x of j, plugging in more indices to it to represent Laplacians, and then that is going to be u of x of t. That's going to be, of course, with respect to time, seeing how much heat transfer will change over time. It's a very elegant equation when you think about it. And then finally dx, because we need to get rid of the s notation. All right, if you're wondering how to solve it in 1 degree notation, now basically what would happen is that first it'll be represented as a curve equation. Basically, the original problem was, imagine if you were to have a rod, and then the rod has a fixed temperature and in between, fluctuating between 0.8 and 0 with the initial Gaussian distribution. All right, and then basically over time is supposed to approach a linear function due to a stabilization of its non-zero temperature. All right, yeah, and then of course another thing as the equation also created is that also created the initial equations for thermodynamic equilibrium. Since thermodynamic equilibrium basically is when you have two objects. Let's say if we have two rods this time rather than just one rod. Now, of course, if you put them next to one another, in the middle they'll reach a certain equilibrium, and then they'll just keep on spreading out with respect to time. All right, because we have got that over with, now you're probably wondering, well, what's the mathematics behind the rod? Well, what we would do is so this is called heat flow, the heat flow equation, of course. Now, of course, getting back into our good old friend Fourier. Basically, you need to represent this isotropically, and you need to define isotropic medium, or in layman's terms, the rate of flow of heat energy per unit area through a surface. And basically what you need to do is SOM is equally proportional to its negative temperature gradient across it. So like for instance, so it's going to be Q is going to be equal to negative K or kappa, whatever variable or whatever notation you use, of nabla U that is going to be represented equally proportional to its temperature. All right. And then K is going to, now if you're wondering what K represents, because this might be a little bit confusing at first, K is going to be the thermal conductivity of material going throughout time, keep on meeting its equilibriums. All right, and then basically the equation for K, if you're wondering what it is, that's now, but negative K basically just means it's non-zero. And then the equation for it is going to be U equals U x of T, which of course is going to be representing heat flow throughout time, as I just said before. And then Q, the Q operator is going to be also equally proportional to Q of x of T, which is also going to be a vector field as well, representing the magnitude of heat flow at a certain point in space. So basically the point in space is going to be represented by a rod, and then T, as I said, quite a multitude of times before, it is obviously time. All right, and then what happens is, so then as the gradient becomes an ordinary derivative with respect to x being its position, the equation becomes Q equals negative K or kappa of the first differential of U over the differential of x. Okay, and then now after that you need to let Q be equal to Q of x of T, of course representing position in time. And just so you know, if it's getting a little bit annoying to you, very sorry, I just need to let you guys remember that. Yeah, I'm sorry if I didn't explain the Schrodinger equation in this much detail, but yeah. Just so you know, now there is tons more to explain about the heat equations, and it is a truly elegant equation. There are tons of articles about it online. But just for the sake of this video, basically I just simply am just going to say just make sure to account for the radiative loss and to represent in one dimensions, or else if represented in two dimensions, going to get quite a lot more complicated. That's why you don't use double integrals, or even worse, triple integrals in order to represent this. But for our sakes, simply, we can just represent this equation in one dimension with its diffusion coefficient as alpha is going to be equal to K over C rho. And this quantity is going to be called the thermal diffusivity of the medium. The medium meaning thermodynamic equilibrium between the rod and the outside. All right, getting over heat equations and classical dynamics. Now, let's get a little more into other things that it's used for. Now, of course, another thing it's used for is literally just used in vector calculus. So now, in vector calculus, it can be represented as a field, of course, a vector field. And then, well, another way I can represent it is like you can represent it by, let's say if we were to have two particles. Of course, this is getting back to Pauli exclusion principle. All right, we have a gradient of a two-dimensional function, let's say a function of, let's say a double function. Let's say f of xy. And that's going to be equal to x of e to the x. Remember our indices, which is going to be negative x squared plus y squared, because we'll remember, it is in two dimensions this time rather than one dimension, so you're going to need to represent all these vectors in a two-dimensional space. All right. And then now, in order to make things a little bit easier, you can represent this by colors, in case there are some coders out there. But I'm gonna be telling. I mean, who knows? Maybe in the future I might do a little bit of a Python demo. If you guys want that, please say that in the comments down below. All right, so usually, basically, a lot of times a gradient is the easiest way a gradient is used is again heat transfer of a scalar field. But let's get a little bit more into harder differentials. All right, so let's say plotting down trigonometric functions in a vector space, for instance. So let's say the gradient of a function x of y. Yeah, there's no more negative. Okay, actually, never mind. I lied to you. There is negative functions. It's going to be equal to a negative cosine squared of x plus cosine squared of y squared. That's going to be depicted as a vector field that is going to be on top of a. It's going to be depicted on top of a bottom plane. So like, for instance, let's say if you were to have a bunch of arrows that were diverging off into infinity. Well, you can represent that by this function as a three-dimensional multivariable equation. All right. So now that we got that out of the way, all right. Now let's say now of course there are some more applications that you could use this for in quantum mechanics, and some more applications that you could use this for in quantum mechanics is, say, another thing they could use this for in quantum mechanics is, of course, Pauli exclusion principle, but you also could use this for, as the topic of our last video, quantum Lagrangians, in order to visualize things a little more easily. Since of course, Lagrangians, now, even though they aren't that hard, as soon as you get into quantum mechanics, of course, the smaller you get, the weirder you get, So yeah. Now, of course, there are so many more things to tell you in this video, so many. But just for the sake of this video, yet again, I think I am just going to tell you about the Jacobian, and then I probably will end this video. Alright, so just so you know, don't mix it up with the Jacobian derivative. I am specifically referring to Jacobian matrix and determinants. So basically, what is this? So the Jacobian matrix, which Jacobian matrix basically is a function that is represented in vectors and several variables, as explained in our nice book right here, which you should really, really read. All right, and basically, ultimately, in a nutshell, you're taking differentials, second, first, third, and all the way up to the nth and mth differentials of a matrix. Of course, taking a derivative of a matrix isn't that hard to do, but the video is getting a little bit on the longer side. Yeah, so I guess I'm going to have to just explain a little bit better detail. Well, not better detail, but shorter detail. All right, so let's say if you were to represent the Jacobian of a matrix as a matrix of F, of course, just being our function, and then it's going to be defined as a m times n matrix, which means that basically it's going to be this basically just a way to visualize it a little bit better. So in a nutshell, J is going to be equal to the differential of our nice little function of our matrix over the differential of x of 1, sub 1, and then that's going to be keep on going all the way into infinity, all the way up until our nth differential, yet again, as we've explained in our Laplacian. And then what we do next is we represent, then when we're representing our matrix, then that's going to be equal to the gradient of that same function with respect to t. This time it's not with respect to time. Yeah. And then that is going to be going all the way to the mth derivative. And then it gets a little bit crazy from here on out. Basically, it's going to be equal to the first differential of f, and then it's going to be to the first differential of x, and then until the top part of our differential family over here goes to m, while the bottom stays at 1. And then if you go to the right-hand side, then the opposite happens. Our bottom part of our differential family goes to n, while the top part still keeps its indices the same. And then finally, the sum of all of these is going to be equal to the differential of f of m over the differential of x of n. Now you're probably wondering, well, what can we use this radical notation for? Well, we can use it in many, many different things, such as differential maps, of course, of Euclidean spaces. Don't forget the Euclidean spaces. We're not doing non-Euclidean things here, since or else it has quite crazy manifolds. And then we also can represent this, and then we also could represent this matrix in Banach spaces and Fréchet derivatives. I know, I might not have pronounced that correctly, but yeah, sorry about that, guys. Yeah, so I guess we are out of time right now. I hope you guys really enjoyed this video on our journey of gradients, and well, I hope to see you guys next time. Well, see you guys later, and well, goodbye. By the way, and sorry I haven't published much lately. I have been doing quite a lot of stuff this summer, and I hope to publish more fluent. Sorry, not more fluently. near in the future. So, well, I guess see you guys.